I'm going to talk about a topic that's kind of very near and dear to my heart. I've been working with a particular database technology for the last 3 years. I really want to tell you and take you through a use case of the battle scars that we got from using it. And I'm really hoping that at the end of the day, everyone can go home and think about how they could apply this database technology to their solutions. So I guess you're asking yourself the question, how can a person who can only grow a neckbeard stand up here and tell you about how to build databases? And I can tell you I've had about 10 years in software engineering experience. I've been mainly and predominantly working in search technologies and graph technologies, and mainly in the enterprise software field. My stack of choice has come up a few times tonight is C#. And about 10 months ago, myself and 2 other colleagues decided to quit our well-paid jobs and start up a new company called Clued In. You can have a look at us here. Where essentially we're utilizing this Neo4j database, which is a graph database, to really build relationships within a company. Now, it was a funny topic to talk about tonight, advanced Neo4j, because I can only presume that there's no real experts in the audience. So let's become an expert. This is a chart, this is a graph. So now we're all experts. So what I'm going to take you over is why we chose Neo4j. We have no ties to it. Why did we actually choose it? How do we scale this to millions of what they call nodes and relationships? And a lot of the things I'm talking about here, they can actually apply to a lot of database technologies. Also talk about graph multi-tenancy. Multi-tenancy, for those who don't know, is the idea of shoving many people's database or data into the same database. I can tell I've been in Copenhagen long enough because I usually say data instead of data. We're going to talk about something inherently very tricky with most databases, and that's security. Of the relational days, if you've worked with relational databases, a lot of this is kind of given to you, and it's done very well. But with search technologies and graph technologies and all these new databases we can start to play with, there's some real pitfalls that you can have with that. The graph is susceptible to this as well. We're going to show you how we implemented what we call application level sharding. No, this is not something you accidentally do in the toilet. This is something that allows you to scale to huge numbers and horizontally, and give you this confidence that, hey, if the next 100 customers come in tomorrow, and then the next day 1,000, I can scale up with those numbers. We have been in production for about 4 months currently, and I really want to take you through the difference between just playing around with this database and actually running it in reality. And of course, as Marco had as well, just some general tips and tricks, pitfalls to get around as well. I'm not here to sell what I work on, but it does help to know the problem we were trying to solve to understand why we chose a graph database. This is your company. You use all of these different tools, and sometimes they actually span over the same types of problem sets. Code, chat, file storage. These are kind of referred to in the industry as information silos. So what we're doing is we wanted to break these down, unleash and unlock the information in these different tools, and kind of surface it to every single employee. So if we drew it like a graph, it kind of makes sense to use a graph database in the back end. This is the stack that we're running on. Okay, so I basically spent most of my career working in Microsoft technology. So .NET and C# is the main predominant programming language we're using. We're using Neo4j as our main graph store. We're using Elasticsearch as our search or full text, full querying, indexing engine, so you can look up things very quickly. We're using Microsoft SQL Server for aggregations. So a lot of this is used for generating dashboards and aggregated numbers and counts and things like this. We're using a distributed cache called Redis, and we're using a backplane very similar to the message queue that Peter was talking about, where this is the kind of thing that allows you to scale horizontally. You just throw messages onto a queue, and as many workers on the other end will say, yep, I'll take it, I'll take it, I'll take it. If you want to scale, you just add more boxes in, more people to listen to those messages. And finally, we use SignalR as kind of a push notification system. This allows us to push to phones, push to the web browser, instead of waiting for requests. And I'm sure a lot of you know a lot more about that because of Marco's presentation as well. So then let's just drop Neo4j for a second. Why do we need a graph database? Well, we wanted certain things. We wanted to be able to search the graph. We wanted to be able to search relationships, okay? We wanted to extract relationships automatically. Translation, this essentially means that we want to take dumb, raw text and extrapolate intelligence out of it. And those intelligence pieces, they usually end up in being nodes connected in some way. An easy example would be documents connected to authors via a relationship of author or created by. We also wanted something that would allow us to drive intelligence to people instead of, I guess, think of this more of the proactive approach of pushing information to you, whereas search is much more the reactive approach. I need to find something, I'll type some keywords in. We're all very used to that. And finally, I want to be able to find relationships between people, between documents, and alike. So when I use a graph technology, it's inherent that paths are something that comes out as a big feature. The ability to walk the graph, walk connections. One of the great things about the graph technologies is that I can find out what Peter and I have to do with each other. And with the data there, we can figure out that we were at the same meetup for Foo Café on this time. That's how we know each other. So it's all about building relationships. I'm so glad no one from Neo4j is here. Because I want to give you the reality. I want to give you this kind of cheat sheet, I guess you could say, for what to look out for and what were the pitfalls. So, of course, like any database technology, there are good parts and there are not so good parts that need thought and more work. I could have said bad, chose not to. So the good parts. I've worked for an enterprise before, and I've worked for a vendor. So I know that this may get into some demo reels or videos of telling the world how good Neo4j is, but I'll try my attempt at it into the camera. Neo4j is the easiest database in the world to just pick up and run with. I'm kind of expecting my check in the mail anytime soon, but kidding aside, it is literally the easiest technology from a database perspective to just pick up and play with. There's lots of reasons why. First of all, easy install. It's just a double-click install, runs on all different platforms. If we jump down, it's got this fantastic web UI where you don't have to jump to documentation. It's just all within the web app itself. If you want to create a graph to start working with, the actual graph they ship with is a movie database, something that kind of everyone can relate to. And they map all actors to movies, and it's really interesting to actually start to find these relationships. The data modeling, I think it's one of its biggest strengths, and it's because it's quite natural for us to draw things and draw connections to them. So you can easily transform kind of like a business model into something that is actually, that's how it's physically stored in the graph as well. I always applaud database technologies, especially that have fantastic documentation, and Neo4j have definitely outdone themselves. Not only is it well documented, but when we're all helping each other out on the internet, we're solving problems on Stack Overflow or something like this. Neo4j allows you to run what we call gists online, which are just, no, you don't install it, don't have to learn it, just run this online. There's ways to run it online to see the solutions, and people can just do this for you. There's a language for querying, and most of you may have heard of SQL before. It's the kind of stock standard way of talking to relational databases. The last time I gave this presentation was about 8 days ago, and since then, this language called Cipher, it's a very intuitive way to walk connections. In fact, for the nerds in the room, you'll absolutely love it because it's kind of ASCII art that you draw to run queries against the database. Cipher is now, even though Neo4j or Neo Technologies own this has been open sourced. This will now be the de facto language to query any graph database technology from now on. So you can kind of guess that because Neo Technologies were the ones that kind of came up with this, that they've got a kind of stable and solid product to back it up with. I've already alluded to the fact that it's got a fantastic web UI. So, the not so good parts. Any database needs some tips and tricks. And one of the common tricks that databases use to speed up querying are indexes. And the way you can think about indexes is that it's just like the back of a book. Someone's done already the work to say, this word is on this page, this word is on this page, oh, and I've also counted them for you. It's exactly the same thing. And underneath Neo, they have this technology called Lucene. Without you knowing it, Lucene actually runs most technologies underneath these days. It's a very solid and well-proven search indexing technology. The bad part is that the implementation of it in Neo4j is just not very good. And it really starts to sting yourself when you get out of this proof of concept phase with a database, when you get out of this phase of, that's a cool feature, let's actually use this in reality. There is a lot of work that needs to be done on this. And I'll give you an example. A common data structure that we all use is arrays, right? I want to be able to look up something in the database by an array property. Here's an example where Neo4j doesn't use the indexes to do those lookups. And hence what it results in is what we call table scans, where it just scans the entire database to try and find what you're looking for. This is a bit weird because if I go back, I said data modeling is a good part. And now I say it's a bad part. And the reason it's bad is because when you're playing with new database technologies, the tutorials, the guides, the samples, they all give you these kind of very limited data sets, but they don't reflect reality at all. For example, the movie database that comes with Neo4j out of the box. You've got these very small nodes where actors have a name and an age. We all know that it's going to have a lot more properties on that. It's going to have a lot more relationships coming in than just acted in. So what happens is that we fall into these traps where we use our POC minds to model the data, but in reality we have to do some really weird things to actually get this out. I'll show you what an example is later on. Who here is a developer that's worked with a NoSQL database? Okay, so we fast forward, actually we go back to the future, let's just say 5-6 years. And the NoSQL kind of database, they started to come out, and there was a lot of word about, hey, just throw it in. Just throw it in these databases, they can take it because there's no schema, and they take any type of objects, and they scale to huge numbers. The fact is that when you do scale any of these technologies, you realize pretty quickly this is not the fact. And Neo4j is kind of exactly the same, whereas when you start to pad it out with more data, you start to run into some issues at scale. I'll be going over these a bit later. And like I said before, think about the problem set that we're trying to solve at Clued In. We're trying to map a company's internal data in the tools that they use. And I see that as real life data. There's people with lots of properties, people with lots of connections to them. Think about everything you've ever worked on at work, and you can think of that as a connection or a relationship to you as a node. That's quite big. In fact, that's in the Neo4j or in the graph industry is referred to as dense nodes, where you've got lots of things pointing to you. And there's some real problems. I'll show you some solutions on how to get around that. But I would actually say that Neo4j, I'm kind of giving them a bad rap with this because a lot of database technologies actually do this. It doesn't feel like they've tested on real life data. For the people who laughed, I think I know I've been in the same situation. So what I want to do is give you this cheat sheet. And I've broken it up into 4 separate topics, which is indexing, performance, profiling, and security. And I'm hoping that this will save you from a lot of those pitfalls that you won't only get if you're playing around with Neo4j, but other technologies that are similar as well. If you've worked with any database before, indexing is essential. And Neo4j, although it does have its pitfalls, at least allows you to have indexes. And there's 2 predominant ways of doing it. The first is kind of this data integrity approach. In relational databases, you don't want the same row with the same ID going into a system. You want some data integrity so that something quite unique, like an email address maybe, that there's no 2 jim@microsofts.com in the system. There's only one. We refer to that as data integrity and typically use constraints for that. You get that with Neo4j for free. And the great thing about it is that while trying to be really good with what goes into this data store, you actually get indexes for free when you start to put these things in. So if I was to say, please put a unique constraint on email, in Neo, I would instantly be able to look up anyone in an index. It would get that for free on the email property. I absolutely applaud this because this is kind of hard to see in a lot of technologies. And that is the profiling that comes out of the box with Neo4j. I referred to this query language before called Cipher. This is Cipher. You draw little circle nodes. You point in directions. Here is your relationship, and here's the other node. So this is kind of a simple one where all I'm doing is I'm saying, okay, well, I want to get A out, which is the name, and I want to find everyone who acts in a movie where the genre is action. Right? So it's quite fluent to read this. If you stick profile in front of any of these queries, it'll actually give you what's called an expression tree. An expression tree is something that we were talking about before with the functional language, this idea of link, LINQ, which is in the .NET framework. Essentially what that is it's a way for you to fluently build these queries that actually just map to something like this anyway. So what happens is when you stick profile in front of what you think is quite a suspect query, it could be doing some naughty things. In fact, what it does is the web UI gives you a breakdown of every step that this is going to call in the underlying Java API. So Neo4j is a Java technology, and you can think of this as the abstraction layer over querying it. This is available from .NET, it's available from Ruby, it's available from all different types of languages. It's essentially a REST endpoint. Now, in later versions of Neo4j with the indexing, Isn't it funny that all of these NoSQL database tools came in and they said about no schema, but all of them are bringing schemas back. And there's one main reason: performance, right? There is other reasons, such as there are some things like sorting of dates and of numbers that you just can't do properly if you don't have schemas telling a person that, hey, that age field or that age property, it's an integer. It's not a string. And because we're using Lucene under it to do all the indexing magic and full text querying, you definitely need a schema. So that's a great move from Neo4j. Unfortunately, they've dropped some features to bring this in. And they've now got they've split the indexing into two parts, one called schema indexing, one called legacy indexing. And I don't know about you, I don't really want to use something called legacy indexing. So performance. You're working with a graph. It's completely different to a relational database. And there's this weird thing that happens when you start playing with the Neo4j web admin, you start writing some queries. You start to realize that this thing that relational databases and document databases are really bad at, joins, are really good in graphs. In fact, that's mainly why they were built, is to embrace joins in systems, and they are extremely fast at that. I guess when you start to play with the graph, the first thing is path queries. What do I have to do with this object over here? What's the shortest path between me and that company? What are all the shortest paths between me and that company? Really cool features, right? When you start to scale with Neo4j, you can't really use these features anymore. And a lot of it's to do with your data modeling, the way that you model your data. But essentially, you've got to cap how far you go out in depth in all of your queries. That really, it stops these features from working. And if you do have these really expensive path queries in production, the way that they show themselves, they actually lock the process, and you'll actually see your CPU spikes just kind of stay at this solid number. For some reason, we'd always have it stay at about 20% of the CPU, and we would just never get that CPU back. And what it's doing is actually, Neo4j is just continuing to try that query. And there's a really easy solution for that. When you're setting up Neo, and in fact, per these Cipher queries, you can actually append a timeout on every single query. So if a query runs, and it runs past 5 seconds, can you please stop that? Because it's just going to kill the system. So at least they have a workaround in there. Watch out for them. It's so funny when I talk to people about, like Elasticsearch or Redis or these very highly scalable database technologies, and people complain how much RAM they chew up. I think it's fantastic. If you are running Neo on your local machine, you get the Chrome experience, right, where it just steals all of your threads. It steals all of your CPU. The great thing is Neo has shipped the product with local kind of settings for your developer machine. So it doesn't do that, right? But when I dedicate a database box we're running in Amazon, and if I buy a micro machine or a 4 gig box, yeah, I kind of want you to use the whole thing. And you can really start to tweak lots of the things. I did say it was a Java app. So of course you've got the ability to tune the JVM. You've got the ability to tune heap sizes. I could tell you right now, when you move a product that you're building on Neo4j from your local machine into a production environment, you will start to kind of shout and want to kill that database. But essentially, really, straight away, there's 3 things that will give you instant performance, and that's increasing the number of web server threads. After all, this is a very high read, high write system. You need threads to be able to do that, and you can tune this. So the defaults are great. It's great for a single machine. We don't go crazy thinking it's just stealing all of our performance. Now, I've been mentioning Java. I've been mentioning Cipher. And I've been mentioning that we're on .NET. So something doesn't compute there. The great thing is that there's a really good .NET library. And it was built by a guy in Australia. And it's quite old, actually. It's 2 to 3 years old. And the really good news is that as of about 2 weeks ago, they've reopened this, and people are starting to contribute to this online. And I give this client 5 out of 5. It is really well done. There are a couple of things to watch out for. First of all, Neo stores all its nodes and relationships in JSON format. Right? And this particular library is quite verbose, I could say, in that when you go to fetch out nodes, when you go to fetch out results from queries, the JSON is huge. And you don't need it all. And like we alluded to before with the maps and the selects that we have, just make sure that you project out from your queries only the things you actually need to process or that show in the user interface. Connections. Now, what I mean by this are not relationships in the graph. I actually mean kind of network connections. When you ask Neo, hey, I want to connect from this .NET library to Neo, the connections are really expensive. And if you look at the wiring of the Neo4j client, it's doing some really weird things. Easy fix. Just cache the connections. Don't have to connect to this every single time, right? And the only time you would clear this cache is if there were network errors or you couldn't seem to ping the Neo4j server. Okay, so maybe there's a connection issue. Clear the cache of this connection and just try and reconnect again. And I think it's coming up. I've got some examples of some Cipher queries we wrote, which are just huge. And what this .NET library gives you is a link wrapper. So it's essentially, for those in the .NET world, it's kind of an iQueryable layer over Neo4j. So you get these kind of iQueryable predicates like where and select and all of these functions we were talking about in a previous presentation. The thing is, this is 2 years old, this library. And Neo4j are rocketing. Just last week, they got another $20 million in funding. And you can imagine that they're changing this Cipher language and adding new features all the time. And this library just wasn't keeping up with it. So instead of using this lovely Fluent API, link-like API, we actually just went back to writing the raw Cipher queries and just running it over to Neo4j and just using a deserialization library to turn it into strong objects. However, it's actually really expensive to do this as well. And I'll tell you why. If I go back, this here, I explained this as an expression tree. Every time you run a query against kind of any database technology, it needs to unravel and understand what this is actually supposed to do. That takes time. And the good thing with writing link queries is that they're cached. They don't have to reevaluate the expression tree every single time you run a query. And all I'll say is that this .NET API has an extension method to cache the expression trees. And I would really recommend using this. So, data modeling. It kind of feels intuitive to data model on a graph. You've got things pointing to other things which have relationships to other things as well. And I would say that the key to getting it right is actually to kind of forget the relational model. Because if you were to kind of take the graph and compare it to a SQL kind of data model, you can think of it as huge amounts of tables with huge amounts of what we call join tables, where it just kind of has the ID for this table and the ID for this table, so it can join different tables. So kind of, you need to think differently when you're working in the graph. Think joins, think that, okay, relationships with really small nodes is what I should be doing in the graph. This is a super interesting one. I alluded to the fact before that the data that Neo4j have tested on is very small. Authors or actors with names and ages. It doesn't really show any realism to production grade systems. And one thing we found out really early on with Neo4j is that, well, first of all, it's really bad at heavy nodes. Having these nodes with lots of properties on it, it's just not good at it. What Neo wants is huge amounts of nodes, huge amounts of relationships, really small. And that's beautiful. It runs absolutely beautiful. So what we found ourselves doing is splitting out our data model into these very small, finite nodes. But what did this mean? It kind of killed this beautiful idea of our data model, where suddenly we didn't have actors in movies, we had actors which had properties, which had other properties that linked to movies. And this is how we were able to get our performance. One more point actually on that. We refer to storing things like images and videos as blobs. You have a blob store. And you have technologies, I guess, like SQL table storage that are built specifically for this. They're very cheap to host relatively dumb data. You can't do anything on the data. Please do not use Neo4j as a blob store. And why? It's the deserialization and the serialization. When it goes to pull things out of the database, it just dies. Okay, now, I alluded to the fact that relational databases were pretty good at security. And it's because most of these technologies allow you down to the field level read or write permissions. And in fact, you can even set different users and different roles at that level. So it's very finite, it's very granular, that those permissions that you can apply. Guess what? In Neo, it's completely up to you. Now, Neo give you a network security. So they give you basic authentication, username and password, and sure, that gets you far, so you can block at the firewall level. But when you're going to query, for those who have kind of solved security in big database systems before, you'll know that you typically have kind of two opportunities to apply security. One's at write time and one's at read time. And no matter which direction you take, they're always going to affect the query in some way. If you take the write time, it's more about writing read and write permissions into the graph. If you take the read or query time, it's kind of gross, because what you do is you query, you get everything back, and then in memory, which is quite fast, you start to null things out. But that screws with things. That screws with paging, with numbers, with counts, with aggregations. And so it's not really a solution. So what did we take? We took the right approach. Not spelt the way that you're thinking. We took the WRITE approach. I can see how that can be confusing. Now I talked also about this multi-tenancy idea. Can you imagine Apple and Google's data in the same system? This is multi-tenancy, but at the same time, you better make sure that that's either secure or you have the option to split them out into different subgraphs. Neo4j does not offer the second option of subgraphs. What they do offer is labels. And labels are these tags, essentially, where you can tag nodes with and relationships with something. It could be product. It could be, this is a TV. For us, it's the organization itself, so the company ID. So whenever we are searching the graph, we built this abstraction layer which always makes sure it appends these extra steps and extra filters, like only go these types of paths that are marked with that organization. I can tell you now that overhead is nil. It's nil. So it really does work as a solution. This is a really interesting thing that we found out, is that what about subgraphs? And what makes the difference between a graph and a tree? When you think about a file system, it's kind of a tree. You've got folders within folders and files within those folders. Now, one interesting thing about my beautiful chart, or graph, sorry, is that these lines refer to relationships, but guess what? They can have directions on them. And this is exactly how we solved the hierarchy and building read and write hierarchy into the graph. Because what we could do is we could find the entry point of what a person's needing to look at. And we can evaluate the directions of the hierarchy we've built into that graph. If you don't have read permission for that folder, well, guess what? We're not going to evaluate anything below that. And this was a really interesting thing that we found. You don't intuitively think, oh, graph, let's just make a tree here at the same time and use the directions to enforce this kind of hierarchy of security. Now, there's different levels of scale with Neo4j. In fact, they always talk about 3. They talk about millions of nodes, billions of nodes, and quadrillions of nodes. And this is how we scaled horizontally. And that typically means that if we wanted more data in the system, we just have to put up more boxes. We don't have to move data. We don't have to get these huge machines with huge specs, huge amounts of RAM. We can actually use these very low spec machines to do it. So right now we're running on AWS, and there is a Docker image for those people who know what that is. Essentially, it's kind of like a lightweight template to install applications and have them run in a siloed manner. And it's built from Neo4j. If those of you who have worked with Docker in the industry, you'll know there's a lot of crap out there. If you go to NPM or any of these NuGet libraries, there's usually a lot of crap that's not well maintained. But it's always reassuring where the actual company that builds it releases their Docker image. And for some reason, when we first went into production, these boxes would just always come down. And it comes back to this whole hungry Neo4j thing. That we were using the smallest boxes available on AWS, obviously trying to save costs, whereas really, these boxes, they need at least about 4 gig of RAM to do any decent size of work. And the great thing is, Neo have calculators on their website. You pump in the number of nodes, you pump in the number of relationships that you would expect, and it will say, yo, probably need about 16 gig of RAM on this box. Now, let's talk about clustering. I hope this is a whiteboard, because I can't draw either. Okay, so clustering in Neo4j works like this. The smallest cluster that you can have is 3 nodes. And the way that it operates is that one node is a writer, and the other nodes are readers. So what this means is that if you've got your application up here, when you're inserting data, there's only one server that actually writes to the database. It's this one, right? And it just so happens that's also the master server at the same time. And Neo in the background says, oh, I'm going to do all the syncing, so all of these boxes are always in line. They always have the same type of data. After all, Neo4j is what is called an ACID-compliant database using transactions, so it does a lot of this in the back to make sure that if something's written, all the other nodes have to have that data in their databases as well. It's relatively easy to set up. this cluster. The guides on Neo4j are fantastic. And I guess the way that it works is that in your application, when you're reading, of course, it only goes to these particular servers. And one of the things in highly concurrent systems, where you're reading a lot and writing a lot, is thread contention, is thread context switching. So if you've got these boxes that are just kind of told, hey, all you do is write, all you do is read, they can definitely optimize their threads to make sure that they're not switching out into things that they should not be doing. So from that point of view, very fantastic. However, from a network perspective, you need to shove some type of proxy or load balancer in front of this, so it knows when to write, and of course, in a round-robin approach is kind of always the recommended. We use a technology called HA proxy, pretty solid, it's free, lots of configuration. You can set up different types like sticky sessions and as I alluded to, round-robin. And they have a really cool feature that they built specifically for Neo4j. I'll bring that up in a moment. So when we moved from our development environment to our test environment, which the test environment was just on a box that I was standing on, into the cloud, there's really no difference. If you take a technology like Elasticsearch, there is. And in fact, if I was to say that there's one technology that does this better, clustering, it's Elasticsearch. And I'll tell you why. And it does actually, it's actually weird at the same time that Elasticsearch just kind of says, I'm going to find everything automatically. So if you're there, I'll connect. So there's some kind of odd things that can happen. So let's ship into the different ways of scaling. Millions, billions, and trillions. Millions is about this. Billions is about having two of these, but just making sure that you're hitting the cache more. You're getting more cache hits than more cache misses, and you do that with load balancing. The final way is to use your data model to actually put things into different shards. So have this 50 times, and then just use something like maybe organization name, maybe organization ID. Say, hey, listen, if you're in this ID range, you go into this shard. This allows us to just scale forever. So, last slide, common trip-ups. Make sure you're profiling your data. I've shown you that with the profile Cipher. Security, you have to handle that all yourself. Path queries could potentially kill your performance if you're doing these very broad kind of experiments. Please don't use the graph as a blob store. Small, finite nodes, huge amounts of relationships, it will run beautifully. Dense nodes, i.e. Justin Bieber, why did I use that as an example? Very dense nodes, unfortunately. Lots of people watching him. That's a dense node. There's some huge complexity that happens around evaluating all of those paths. And I won't do this slide because this was my rant to the Neo4 engineers, and they were here at the time, and you don't want to hear that. So thanks for listening.